Okay, so welcome to this lecture, and we're gonna spend a couple videos on the metrization theorems. Okay, so forgive me, this is my second time recording this. It's just some glitch that didn't make it, so I might be less patient. Okay, forgive me. So recall that we've proved the horizontal metrization theorem that regular and second countable implies metrizability. But we want to know that when is this, what condition is equivalent of being metrizable, right? Because in the horizontal theorem, we really need a regularity, but the countable basis is not that much needed as the regularity. So we want to find some condition that's weaker than second countable. And it must be just right, okay? So it is figured out by the mathematician Nagata and Smirnov. They come up with the definition of being locally finite. So a collection is locally finite if for any point x there exists a neighborhood such that only finitely many elements in A is not disjoint with them. So it intersects with only finitely many of A's. Okay? And this is the definition of being locally finite. It is locally there exists a neighborhood such that is only finitely many A such that it is not empty. And if a basis is expressed as a countable union of locally finite sets plus regularity is in fact equivalent of being metrizable. So for this video, we're going to focus on the local finiteness. So here are just some examples. You may just take a look of locally finite sets in R, right? And this one is also the same. And we have a lemma that for a collection is locally finite, then any sub-collection is locally finite, and the collection of the closure is locally finite, and then we have this equality holds. Part A is trivial, and for part B, we have if U is open and U and A bar disjoint, then this is disjoint. So, I mean, this is the proof here. Okay, so from here, if we have this, then this shows that B is locally finite, right? Because if you intersect with infinitely many of A bar, then you will intersect with infinitely many of A's. So from this, we can show that B is locally finite, given that A is locally finite, okay? And for part C, let Y be the union for convenience. And we have this is true in general, so we want to show the reverse. Okay, so we pick X and Y closure, and we pick a neighborhood such that intersects only finitely of them. And now we're going to do something. First, we made a claim that X is in finitely many of them. So suppose not, then this will be a neighborhood of X, right? Such that it is disjoint with any elements in A. Why? Because for those A is not equal to AI, we already had this is true, right? But for those Y, if Y is in some AI, intersect with this, for some I from 1 to K, then this is a subset of this, which is a subset of this, which is empty, so Y is in some empty, so which is a contradiction. Thus, we have this is true, right? Because you're disjoint with all the A's. Okay, you're disjoint with all the A's, then you're disjoint with Y. But we have X's and Y bar. This is a neighborhood such that it is disjoint with Y. But we have X is in Y bar, which is a contradiction. Thus, you are in finally many of them. And then you're in the entire union. Okay? And we made another definition that is called countability locally finite or sigma locally finite if it is a countable union of locally finite collections. First, I have to make sure to let you know that countable sets are locally finite and locally finite are sigma locally finite. Okay, you have to verify this on your own. Okay. And another definition, say for two collections, we say B is a refinement of A if for any element in B, there's this element A such that B is contained in A. Okay, and just if it consists of open or closed sets, we call be it open or closed refinement of A. So here's a definition. We say, okay. We say a non-empty set with a partial order is well ordered if any non-empty subset has a minimum element. Okay. And it turns out that axiom of choice is equivalent of well-ordering principle. Is that axiom of choice is equivalent with any non-empty set has a order that is a well-ordering. And we're going to use this fact. The proof for this is included in my linear algebra lectures. Okay, so if you're interested for the proof, you can go check it out. But for the sake of time, we're not going to prove it here, okay? And the lemma we're going to prove is that any metrizable space and any open cover of it, there exists another open cover such that it refining A, and it is sigma locally finite. To do this, first we pick a well-ordering of A, and then we pick a metric, and we pick a positive integer, and we pick in U and A. Okay, so let's just first set up everything right now. Now we're gonna let S and U be all the X such that the 1/n ball is still contained in U. So this is a subset of U. Okay, and then we're gonna use the well ordering of A. We may define T and U as S and U delete all the union of all the V that is V less than U. So to make this clear, here's the situation. Okay, you might read it out. You might pause and take a look. I mean, actually pause and take a look. Okay. And we have a claim that V is less than W, then any two elements of V, T and V and T and W are 1/n apart from each other. And the proof is here. So you might just take a look. It's not that hard, right? You're in T and V, then you're in S and V by definition, which means that we have this. And on the other hand, Y is in T and W, which means that you are in this, but you're not in this. But remember that V is less than or equal to W, so you're not in V, which means that you're not in V. This isn't contained in V, and Y is not in V, which means that their distance must be at least 1/n. But our T and U constructed are not yet open, so we want to expand them to make them open, but not expand it that much. So we're going to expand T and U to E and U, where E and U is all the 1/3n balls of X for each X in T and U. Okay? So now we have another figure. Okay? As the figure suggests, the sets we have formed are disjoint. Indeed, if V and W are disjoints, right? Then we have this is true, and the proof is in here. It's just by triangle inequality. And also V and A, then E and V is contained in V, and the proof is in here. Okay? You may just pause and take a look. Okay? So now we just let epsilon n as all the E and U were U and A. So we have a second claim that it is a locally finite open refinement of A. First, from here we already have is a refinement, right? It is already a refinement. For any E and V, it is contained in some V and A. And each E and V is open. So this is checked. We want to check if it's locally finite. Okay? Well, for any X, this intersects at most one of epsilon n because we have these two sets are 1/3n away from each other. So this intersects only at most one of them. If it intersects two, we can use triangle inequality to get a contradiction. But as you might guess, we want a union with all of them, right? We want to take a union of all of them. All the epsilon n where n is a positive integer. So epsilon covers x. Why? If we have this, we have a claim that epsilon covers x. Let's just verify this first. For x and x, we're gonna let C be the collection of all the u and a such that it contains x. Okay? And then this is not empty because a covers x, and we pick u as the minimum of it, right? By the wall ordering. Well, A has a wall ordering, right? Any non-empty set has a minimum element. As U is open, we can pick a 1/n ball in U, because U is open. Thus, we have this. But U is the minimum of this. U is the minimum of this. Thus, X is in this, subtract by this, which is still in T and U. Why? Because for any V less than U, if V is less than U, then X is not in V, right? Because if we have X in V and V is less than U, which is a contradiction, right? But U, like, it contradicts the fact that U is the minimum of it, right? So X, this is being safe, right? It is still inside. It is not in any of the V's, right? Which is still in T and U. But T and U is a subset of E and U, and E and U is in some epsilon n, where epsilon n is a subset of epsilon. Okay? So we have epsilon covers x. Is that for x and x, x is inside some E and U, which is inside some epsilon. Okay, so we have epsilon covers x. Epsilon covers x, which is this. So epsilon is sigma locally finite, right? It is open, right? Each element in epsilon n is open, so it is a countable union of open sets, which is a collection of open sets. And epsilon is a refinement of A, right? Epsilon is a refinement of A because epsilon n is a refinement of A, and by the definition of epsilon, right? I mean, this is kind of stupid to explain even more, right? If we have B that is in epsilon, then B is in some epsilon n, right? Then B is in some V that is in A, right? So we're done. Okay, so we're done with the lemma here. Any metrizable space in any open cover has another open cover that is refining it and is sigma locally finite. Okay, so this is it, and we'll see you guys next time.